what we're going to cover today is a topic called scatter plots, which deal with the concept of data trends and causation. And what we want to do here, and to put it into perspective, it's included in the topic of linear equations. And what you've done so far is figure out whether you have a linear relationship or not by looking at equations, looking at graphs, looking at a table of values or a set of um, points. And what we want to do today is look at actual situations or actual ordered pairs that do not necessarily give us a perfect linear relationship, but are close enough in a linear relationship that we can come up with and figure out the equation of a line that best fits it. What we're going to do today is understand a little bit about what this topic means, and we're going to do some of this by hand. And then the next lesson, we will be using the calculator to get a more accurate picture. Now, what we want to do is let's go through some of these definitions here. A scatter plot is a graph used to determine whether there is a relationship between paired data. So what that simply means is we would plot a relation, a group of ordered pair, and we can figure out by just looking at where the data lies, the data points lie, whether there is some sort of linear relation or not between the data. Now, correlation and causation. And when I give you an example, I think it'll be very simple to understand the difference between the two. Correlation is just trying to figure out, is there some sort of relationship between the two pieces of data? Causation is when one data directly causes or impacts the other. So let me give you a very simple example. Studies have shown that people who own red cars are twice as likely to have an accident. Now, does red cars by themselves cause accidents? No. But insurance studies have shown, and when they trend the data, that if you own a red car, if you're an owner of a red car, you're more likely to be in an accident. Okay? So all I need to do is analyze and look at the data, and I can see that that relationship exists. Now, causation, a couple of examples there. Smoking causes lung cancer. Exercise causes you to burn calories. So those are two examples where you can see that one event definitely causes the other. And the thing with causation is, as opposed to correlation, causation, you need to actually prove scientifically or otherwise that one causes the other, while correlation, all you need to do is look at the data trends. Okay? Two recalls, independent variable is the input, always plotted on the x-axis. The dependent variable, the output, always plotted on the y-axis. Okay? Now, when you do your scatter plot, you have three possibilities: a positive, a negative, and no or little correlation. What does a positive correlation mean? Y tends to increase as x increases. They're going in the same direction. And you could put it in the converse, which is they both decrease. A negative correlation, y tends to decrease as x increases. And again, that could be flipped around. And you'll see I'm always starting with y because it's y that is the dependent variable. And then little or no correlation means x and y have no apparent relationship. Now, a lot of times when you look at what the data is we're comparing, it becomes somewhat obvious as to what the situation would be. Okay. Now, we have what's called the correlation coefficient. And you're going to see this when we do it on the calculator, but just so that we understand what it is. The correlation coefficient tells us specifically how strong a correlation is between the two pieces of data. Okay? And it's a very simple concept. The range of the correlation coefficient is from 1 to -1. And -1 means there's a strong negative correlation, and 1 means there's a strong positive correlation. If you're exactly at 1, then it means you have a pure linear relationship. Okay? So what we're going to do is we're going to do two scatter plots, and we're going to see what type of, in the first one, what type of relation there is. And in the second one, we're going to do what's called a line of best fit. All right, so we have a scatter plot that shows our data listing of the altitude of an airplane and the temperature outside the plane. Okay, so hopefully you realize that, and I'm just going to scroll this up a little bit to make it a little easier to work with. Hopefully you realize that altitude is your independent variable and temperature is your dependent. I'm just going to put the word temp there for now. So looking at the altitude, we go from 0 to 5,000. So I'm going to count by 500s here. I know it's a little boring just watching me write numbers, but there is no other alternative. And then for temperature, I go from almost 0 up to almost 60. So I'm going to count by tens here. And it's frustrating how easily this board loses its orientation. So now I'm just going to plot the different data points. And it's going to be again, as close as I can possibly be. Because you'll see the numbers aren't going to be exact when doing this. $1,500 is 55 and a half. 2,000 is 41.6. Wow. Well, take a minute so I can reorient the board, because this is very poorly oriented, although I did it before I did all of this. In case those of you are asking, why didn't I orient before I did this lesson? I did, and that's how quickly it gets out of orientation. Okay, so I'm sorry, we're back at 2,000, 41.6, a little better. Still not great, but I'll make do with what I got. 2,500 is 29.8. 3,000, 29.9. 3,500, 18.1. 4,000, 26.2. 4,500 is 12.4. And 5,000 is 0.6. So hopefully you'll see, while not in a clear linear relationship, meaning I couldn't draw one line through all these points, the data set tends to have a negative correlation, since the temperature, which is the dependent variable, decreases as the altitude increases. Okay. Okay. All right. Now let's take the next example. What we have here And again, you should be able to make some judgments just based upon the data and looking at the data set. I want to graph the relationship between the age and the weight of a panda. Okay, so I have age here, weight here. Age goes from 0 or 1 to 12. And weight goes from up to almost 60. So I'm going to graph my data points. Hopefully my orientation is pretty good. So at age 1, I'm at about 2.5. Age 2, I'm at 7.6. At age 3, I'm 12.5. At age 4, I'm 17.1. At age 6, I'm 24.3. At age 8, I'm 37.9. At age 10, I'm 49.2. And at age 12, I'm 54.9. Now, obviously you could see that there is a positive trend here. And what I want to come up with is and write what's called the trend line or line of best fit. Now, what ideally the line of best fit would do is go through at least 2 points, and it would have as many points on both sides or an equal number of points on both sides of the line, or as best as possible. So doesn't work perfect because my orientation's off a little bit, but I'm going to draw, I'm going to come up with a line of best fit that's going to go through the points 2, 7, 6, and 3, 12.5. So, and you could be using a straight edge ruler for this, but something along these lines. Okay? So I went through the following 2 points, 2, 7.6, and 3, 12.5. And going through those 2 points, I got a pretty good distribution of data. It looks like some are a little bit more on the left side than the other, but it's pretty good through there. Okay? So now I want to come up with an equation for this line. Well, how would I do that? Well, first is I find my slope. And I find my slope to be 4.9. Now, as we've done before, once I have my slope, I could find my y-intercept by plugging in one of these 2 points. Doesn't matter which one. So my equation for what's called the line of best fit, try to move this down, is y equals 4.9x minus 2.2. Right? Now, sometimes these lines, because somebody might be saying right now, well, what you're telling me is my y-intercept is negative 2.2, which seems a little silly because how could I have a 0, at 0 ages, I have a negative weight, but you don't want to look at it in that context because what you're doing here, again, it's not a perfect line. So it's a number that's helping us calculate our data points. So what would a 7-month panda weigh? Well, what I would do is put 7 in for my X value. And so I would expect a 7-month panda to weigh approximately 32.1 pounds. Now, is that exact? No. Is that going to be what every 7-month panda would weigh? No. But I know my number makes some sense because when I go back up to the table, 32.1, sorry what that number was, 32.1 is reasonably close or in between these two numbers of 6 and 8 here. Okay? All right, so to summarize, what we did today is we took a look at the types of correlations we can have amongst data points. We plotted data points, and then we came up with a line of best fit by hand. Next week, we're going to do this using our calculator.